Now let us discuss what should be the magnetic field due to steady currents, and that is essentially given by another law known as Biot-Savart's law. So before I really go into the little calculation of the magnetic field, I should tell you what steady currents are. Okay, so this now I have already given you one expression where I showed you can express your current density, volume current density as di by dA perpendicular. That's your cross-sectional area through which di is passing, right? So the total current passing through any surface will then be given by the integration. Okay, right? So our total current I crossing any surface should be given by J dot dA, and this dA is essentially your cross, so it's your dA perpendicular, right? Now using your familiar integration theorems, you can convert the surface integral into volume integral. J dot dA is nothing but your del dot J deta volume integration. Okay, so far so good. I think you are getting me. Now, what is this current passing through? This should signify, it should also signify how much charge is passing through per unit time, which means this should be the variation of the charge, right? And the total charge is nothing but your charge, volume charge density rho multiplied by the volume element dV, right? D tau. So this is your charge. Now that variation should be captured by this, right? I hope it is clear. Now in that case, okay, so for this, the del dot J will then be given by minus del rho by del T. Okay, this is, so this is known as continuity equation. Okay, now for steady current, when I say steady current, I essentially mean that the current is constant. There is no variation. And to have a steady current, you shouldn't have any variation of the charge as well. Like there should not be any variation of the charge density. So del rho by del T should also be 0. So you are saying the volume, the current density variation is 0. The charge density variation is also 0. That is what I mean by steady currents. And if you consider all of them, like del rho by del T equal to 0, so that essentially means del dot J equal to 0, which means there is no divergence for the current density, or there is no piling up or depletion of the charge, or like there is nowhere the charges are getting assembled, so that will kind of violate the condition for steady currents. Okay, so now that I have told you what steady current is, let us see what should be the magnetic field be due to steady currents. And that is essentially given by Biot-Savart's law, and the expression looks like this. Okay, the magnetic field Br due to a current I, essentially a steady current I, is given by mu 0 by 4 pi I cross r cap by r square dl prime. So what essentially it means? Actually, there should be a vector sign here. Yeah. So imagine a current loop. Okay. So imagine a current loop here, and then this segment dl here. Okay. So we are now dl prime. So you must be familiar with these prime notations. Essentially, the source is given by these prime notations, and where you are the test, you are putting the test charge, or you are putting where you are measuring the measurement point, where is given by non-prime symbols. So r is my position vector of the point where I'm interested to measure b. Okay, here I'm measuring b. That's the position vector is r, and that's my separation from this source element dl prime. Okay, so that's a very familiar setup which you might have encountered a lot of times in electrostatic as well, and the current is flowing like that. So the dl prime direction and the current direction is the same. Okay, for this kind of setup, B, the magnetic field, is essentially given by I cross r cap by r square. Okay, we'll talk about this proportionality constant mu 0 by 4 pi, where mu 0 is the permeability of the free space. Okay, some proportionality constant. So now if the current is steady, you can take them out and then put the vector sign on the, because both I and dl are in the same direction, so you can happily write dl prime cross r cap divided by r square. So br, the magnetic field, is dl prime cross r cap by r square. So mu 0 I by 4 pi is outside of the integration. Please remember this expression. This is a very important expression to calculate magnetic field for a current distribution. Sorry, for a current loop. Okay. Okay, so let us take an example and see how we can calculate magnetic field for a certain current. Okay, steady currents. So first, one of the simplest example we will take. Let's imagine that there is a line, pretty long wire carrying a current I. Okay, a long segment of wire which carries a current I. Now we are interested in calculating the magnetic field at a certain point P, and the separation from P to this wire is S. So as usual, so we consider a segment dl prime at certain place, and then the separation from P is given by your separation vector r cap, sorry r, and the angle it makes is theta. So what essentially we are planning to do to calculate B? All you have to do is to calculate this particular factor dl cross r cap by r square. These are all constant. You know I, mu 0 I by 4 pi you can estimate. So the problem boils down to calculating the cross product of dl prime with r cap and of course r square. Okay, what is the separation vector? Okay, so now first let us see what is dl prime cross r cap. So dl is along this direction. Okay, so that's your dl, that's your r. Okay, so your, if this is your alpha, let's say this is sorry, this yeah, yeah, so that's my angle alpha. So in that case your dl cross r should be dl prime sine alpha. Now this is alpha, that is theta. This should be your 90 minus theta. So it is your dl prime. So that if you plug in here, so that should give you dl prime cos theta. Okay, this is a simple geometrical simplification. So your dl prime cross r cap is nothing but your dl prime cos theta. Okay. However, what is your L prime? So that's your L prime, right? Sorry about that. So that's your L prime. Okay. So your L prime now should be your S tan theta. Okay, your simple triangle rules. So now what should be the DL prime then? So you do the differentiation, you should get it, you will get it DL prime as. So that's my DL prime. So DL prime is nothing but your S by cos square theta d theta. Just a simple differentiation. Okay, I hope it's clear. In that case, your and also S is nothing but your r cos theta. So now you have all the things ready to plug in the integration. So you have dl prime across r cap, you know what it is. Then your 1 over r square is nothing but cos square theta by a square. So this is your r. Okay. So if you want to calculate your 1 over r square from this geometry, so you will find out it is nothing but r is nothing, s is equal to r cos theta, so 1 over r square is equal to cos square theta from this expression. Okay, so you calculate your, r cap 1 over r square from this expression, that is cos square theta by s square. Okay, now you plug in all these things to the integration. Okay, so magnitude thing we'll see later. So sorry, direction thing. Let us first calculate what should be the magnitude of it. So then you plug in all these values, and then you have this mu 0 I by 4 pi. Your 1 over r square is nothing but cos square theta by a square. That's your 1 over r square. That is your dl cross r cap, dl cross r cap. So now you do some rearrangements. So what you will undo the integration. So eventually you will find out that b, magnitude of the b, is nothing but mu 0 I. So of course, when you are doing an integration, you are taking it to certain, so you are planning to take the integration limit as uh, okay, something like this is my theta 1, and then this becomes my theta 2, and then you do the integration, right? So for that segment, okay, what is your value b? What about the direction? So again, you go back to this, I'll erase this one for the timing, and then what you see the direction. So if you use your uh, uh, cross product rules, you will find dl cross r cap will point out of the page, okay, on from on the top, on the upper portion of this square, and going into the page uh, uh, at the lower portion. So here in this, so here it will be out of the page, here it will be going. So it will like a phi cap direction, okay, along the where. So okay, this is like that phi cap. Okay, so the for the direction, as I showed you, if P is on the first on the top part of the wire, then there is like it should be out of the page. Now imagine, instead of a finite wire, you elongate this to infinity. So if you elongate this to infinity, this limit, the theta 1 and theta 2 limit, the theta 1 will go to minus pi by 2, theta 2 will go to pi by 2, and you can put back those limits. So theta 1 goes to minus pi by 2, theta 2 goes to pi by 2, when the infinity, for the case of infinity here, and then you will find a very, very, very simple expression for the magnitude of v as mu 0 I by 2 pi s. Very simple. And the direction, as I told you, along the phi cap direction. These are some interesting consequences. Now, so you know the magnetic field due to due to a current carrying where the current is I. So it is mu 0 I by 2 pi s, mu 0 I by 2 pi s phi cap. Now, what happens if you have two wires which carries current I1 and I2 and placed at a distance d? So first thing you should see, each wire will exert. So like for example, at where I1 or where 1, there will be a magnetic field due to where I2. So you just now calculated what should be the magnetic field due to a current I. So what you can do, you can say that the magnetic field at 2, at this where, due to 1, should be mu 0 I by 2 pi I1 by d, right? This is your mu 0 I by 2 pi s, right? The same expression, instead of s, you just put d here, and your current is I1. So this is the magnetic field. This is the magnetic field at I2 due to I1. So then use your force equations. The force is nothing but I dl cross b, and that should give you b, you replace mu 0 I by mu 0 by 2 pi I1 by d, and then dl and b are perpendicular to this, okay? So yeah, so use your dl cross b expression, and then it is easy to see that the force is nothing but mu 0 I1, then I So here I should mention here I2 here. Yeah, I2 dl cross b, and the b is due to 1 at 2. So this I2 multiplied by mu 0 I1 2 pi d dl. I hope it's clear with you. You first calculated b, then you are just using the familiar expression to calculate force. Okay. This force, if you now use your right hand thumb rule, let's say for cross products, you will find also dl direction is along this. So that's your dl. Okay. B is along phi cap, right? So B goes into the page there. Okay. So then dl cross B should actually uh, be directed towards I1, or it's an attractive force. Okay, so the force between two current carrying where currents are running parallel will be attractive, and this dl is you can use infinitely long wire, and then or you can do one thing, you can calculate the force per unit length, so then this dl factor goes away. So all you have is that mu 0 by 2 pi I1 I2 by d. Okay, so that's kind of the force per unit length between two current carrying wire. Currents are parallel, and that's directed towards that's an attractive force. So it will be both wires should be attracted towards each other. Okay, so now let us take another example and calculate the force in a scenario where you have one wire and there is a loop there. So there is a rectangular loop where current is in the direction, in the clockwise direction. Current I is flowing here. Rectangular loop having sides A and B, and it is placed at a distance S from a straight wire. Okay. Now, if I want to ask you the question, what should be the force on this rectangular loop? Okay, due to this straight wire I. Now, first thing you should know is that the magnetic field due to this straight wire here. So on this portion, it will be outward to the page. I have already explained you, right? So this will be coming out of the page at this in this area. Uh, yeah. So as first thing you should see is that the force on this B side will cancel out. That is easy to see. You just use the cross product rules. You will find the magnitudes are equal and the directions are opposite. Okay. So that will cancel out the forces on this B side. I urge you to check yourself. You use the cross product rules and see what should be the force on this B sides and verify that this should cancel. So the force on top and bottom will remain. Now, what should be the force on the bottom side? Very easy. Separation is S. There are, you can think of these are two parallel wires. So it's nothing but the mu 0 I by 2 pi S. The field, so the force will be, sorry, the field will be mu 0 by 2 pi S. That's very easy to see. I have already deduced that. The force, current is I same, so your mu 0 I square by 2 pi S. Again, a familiar expression I have already derived, and integration over dl. Now integration over dl should give you mu 0 I square. So integration over dl should give you A. So the final expression mu 0 I square by 2 pi S. And again, dl is along. So if you look, so dl is along this direction, right? Yeah, this direction dl, right? So you can again use the cross product rules and you can verify that the f direction should be z cap. Okay, towards up. So I have not drawn here the I have not drawn any, so you can, I can just draw the, that's my z cap. Okay, so then you can see that the force on this segment is going up towards z cap. And for the top, you can again do the calculation, and here the separation is nothing but s plus b, right? The s plus b, the separation. And for that reason, the force will be given by, you can again verify this expression here, mu 0 I square 2 pi s plus b. The integration again will give you a there, and that direction is minus g cap. Now, what I urge you is that please verify these calculations and the directions as well using some simple geometrical arguments, and see if this is done correctly. Okay, that's what you should do. So the net force for this kind of wire loop will then be you can just subtract this one from this, and then you will eventually find out a simple expression, mu 0 I square 2 pi s ab by s plus b, and along z cap direction. Okay, so what in this lecture what we did is that we kind of discussed how to calculate the force due to the movement of a charge which is going in a velocity v, and also we discussed how we can calculate the magnetic fields due to steady current. So we took some examples to show for different geometries to show how this can be done. In the next lecture, I will go on to discuss about uh, the curl and the divergence of. So in the next lecture, I will discuss about the curl and divergence of B. I will discuss about Ampere's law and then magnetic vector potential. We'll also solve some problems. So thank you.